Hello, Futures Institute members. We are so excited to bring you yet another thought leadership webinar today. We know that wherever you are around the nation or across the globe, you are tuning into this on demand, and today's topic is super exciting. We're going to dive into an organization called the Mind Research Institute and tell you a little bit about a program called ST Math that really gets at the deeper neuroscience of learning. I can tell you personally, I've got almost 20-year history with this organization, both as a practitioner and as a researcher. And I am so thrilled that you are going to get a glimpse into this absolutely amazing organization. They are transforming the way kids learn and think about math, and they have a huge national footprint. With that, I would like to welcome you to our distinguished guest. Nigel Nisbet is the Vice President of Content and Creation, and we are excited that he's going to lead us through today's webinar. Welcome, Nigel, to the Futures Institute.
All right, thank you very much. So we're going to dive in, we're going to look at ST Math, and it's worth kind of looking under the hood a little bit because it is different. It doesn't work the way that other math programs work, and it's kind of interesting to look at the way it works and some of the neuroscience behind it. But we're going to start somewhere completely different. We're going to start with a meme. I'm sure you've all seen things like this. They've been all over the internet. This one I've seen, there's many thousands of them, and they get viewed a lot of times. And what's interesting when we pick these apart is that, you know, this is the type of thing that I've certainly had a lot of parents come to me and say things like, why can't we just teach math the way I learned it? And really what's going on here is, yes, there's sort of this, you know, sort of new way of teaching, old way of teaching, but what's really happening is really this is the debate about whether we should teach math procedurally or conceptually. And really, it's focusing on this question of how do we teach? But if we're really going to change outcomes for our kids, we need to ask a different question. Instead of how do we teach, we really need to be asking, how do we learn? And about 11 years ago, I walked into a classroom in South Central Los Angeles where I was a district math coordinator. And I saw kids working on a program that completely revolutionized the way I thought about learning. And I saw someone had asked this question, how do we learn? And they'd made significant progress in answering it. And in the late 90s, some researchers at University of California, Irvine, dove deeply into this idea of how does the brain learn? And they looked at spatial-temporal reasoning, the connection between spatial reasoning, music, and creativity, and the connection between all of those things and learning mathematics. And the key sort of fundamental thing they were asking was, what if math could be taught the way that the brain learns? And the outcome of this research was the program ST Math, Spatial-Temporal Math. So we're going to look at this a little bit today and dig in. And it's something that we start with ST Math right at the very beginning. We don't wait for high school to start building spatial temporal reasoning or even middle school. We start way back in kindergarten and even in pre-K. So how do we get kindergarten kids doing spatial reasoning? And we do it something like this, obviously with a penguin. You can see here as I click these moves across the bottom of the screen here, Gigi, the penguin, moves around. And it's my goal here to try and figure out how am I going to get Gigi to match orientations and then cross the screen. So let's play a game. Let's see if we can do this. And maybe I can get some volunteers to give me some moves. So here's a game. Here's Gigi. Gigi is kind of over here, feet up, poking out of the screen. And we need to figure out how are we going to get Gigi to look like this? How are we going to get Gigi across the screen? We've got 3 moves. You'll see there are no written instructions. There are no verbal instructions. These are the 6 different things we can do. Let's call these 1, 2, 3, 4, 5, and 6. So what I'd like you to do, and if I'm looking over here, it's because I see your screens. I'd like you to hold up some fingers. What do you think? Give me a move. What would be a good first move we could do here? You can either type it in the chat or you can hold up fingers to show me. What do you think a good first move would be? What should we do? And remember, this is a question for kindergarten students, so there's no pressure whatsoever. 2, we're going to go with move number 2. All right, fantastic. Now, notice this time nothing happens, not because it's wrong. There are actually 12 different ways to solve this problem. As with a lot of good questions, there are multiple ways of doing it. And in fact, any of these first 6 moves would be correct on the first go. All right, but so imagine, visualize this in your head, because we've got to do the whole thing in our brains. We've got to use that spatial reasoning. Okay, so 2. So what's the next move? What could we do next? What do we think? 3. I'm seeing a 3, a very confident 3. All right, let's see how that goes. We've got a 3, and then we did one more move. What do we think? What are we thinking? Okay, let's check and see. Have we got those kindergartners beat this morning? 1, 2, 3. Oh, fantastic. All right, and Gigi gets across the screen. Fabulous. So it looks like a cute, fun game. You can imagine that young kids would enjoy playing this sort of thing, and they do. But what's interesting here is what's going on in this game from a neuroscience perspective. And it's really worth, as I said, kind of digging into that. What's happening here is something called the perception action cycle. This is not a mind research thing, or this is not an ST math thing. This is a solid piece of neuroscience that's been relatively well understood for a long period of time. And it's also something that we use on a daily basis. Everybody uses this all the time, but we can also utilize this major learning mechanism to actually build mathematical ideas. And it works a little bit like this. Anytime you're confronted with a problem, you use what we call existing schema. Whatever existing neural networks you've got, whatever you've got built up in your brain, you use those to make a prediction, which is exactly what you guys did just now. You made a prediction about what you thought was going to happen, and that resulted in an action. Like you think, okay, I think this is going to be it, so I'm going to choose these moves. And then Gigi takes over, the game animates out. And in this case, just like you guys did, you can see Gigi got across the screen. And we see it, we perceive that. And here's where it gets interesting. In our brain, there's a little piece right in the middle called the hippocampus. And our perception gets matched up against our prediction. Here's what I thought was going to happen. Here's what I see actually happening. And these two things get compared in the hippocampus. And in this case, boom, they match. So the hippocampus sends out some chemical signals, and that schema that made the prediction is grown. Literally, it is made stronger. So the next time you're confronted with a similar problem, it's more likely to fire up. And this is how we build spatial reasoning schemas, proportional reasoning schemas, numeracy, all kinds of things. And we obviously use it to build all kinds of things, maps of the world around us on a daily basis. But we can use these to build these schema. But we don't only learn when we get things right. So let's just rewind that a second. Let's just imagine, what if we'd made a different prediction? What if our brains had fired up a little differently, some different schema had fired up, and we'd ended up choosing some different moves? Well, the game is agnostic to our moves. It's going to play them out no matter what happens. So Gigi tries to get across using the moves we got. But in this case, it didn't work. So again, we perceive that it didn't work. Again, in our hippocampus, here's what I see happening. Here's what I thought was going to happen, and they're compared. But this time, they do not match. And a very different signal goes. So first of all, it says to that schema, not so much. And it kind of deprioritizes it. So the next time you're confronted with a similar problem, it's very unlikely to fire up again. So this is kind of how misconceptions are addressed. The work, for example, of people like Joe Bowler is based upon this idea of, we can learn by our mistakes, because a second signal also emits from the hippocampus, something very important. Theta waves are emitted, and they say to the brain, you need to learn something new. So when you make a mistake, you're literally firing up this mechanism that kind of puts your brain in a mode ready for learning, kind of like, and it's that moment, and you've all had it, when you kind of, you thought something was going to work one way, it didn't, and you get that little moment of curiosity where you kind of go, wow, that's weird. That's theta waves firing up, telling your brain you need to learn something new. Something else really interesting about this process, there's a reason why in ST Math we use so many visuals. Everything starts visually, and we'll see later it transitions, but everything begins visually, because our visual sense, for most people, is the fastest way to get information into the brain in this perception action cycle. Our language is language is a great tool for helping kids to sort of develop ideas once they've got the basic things in there. It's really good for kind of focusing, sharpening our ideas, making us understand them more deeply. But language is a very inefficient way to get information into the brain. Visuals are much more powerful, which is why in math in general, visuals are such a useful tool and widely used. Similarly in ST Math, even more so. So let's just think a little bit about the nature of math then, because one of the problems and challenges is that it's very easy to think of mathematics as a list of ideas, like a list of topics. We see lists in textbooks, we see lists of standards. We think, right, what I need to do is I need to teach this list of ideas. And if I teach all these things, then great, I've covered it. And somehow that's going to magically mean that the kids understand math. The problem is that this is not how the brain actually thinks about or uses or stores the information about mathematics. Our brains would use it and store it a little bit more like this, where instead of a list, it's kind of this interconnected web. And the big difference here, the big deal, is that what's important here, it's not only the fact that, yes, there are these nodes which effectively correspond to the items in the list, but just as important, or perhaps even more importantly than the nodes, are the connections between them. When we say that someone has a deep conceptual understanding of math, we literally mean that they have this rich interconnected web of ideas that they can use to solve problems. So we're going to kind of dive in and look at this a little more detail. So this is kind of what we're trying to build for kids, say in K8 math, right? This is the space, and this isn't a map of the brain. This is a schematic diagram of the way that our brain would have these interconnections. And we're going to look at one area of this. We're going to look at fractions. One of the key ideas here, of course, is that kids should never be learning about a topic through just one angle. Notice we have circular models, we have rectangular models, we have all kinds of other shapes, fractions on the number line. They need to understand how all of this connects together. So let's look at what happens first when you don't do that, when you teach math as a procedure. This is a question that was on the NAEP assessment several years ago. It's the assessment that happens every 4 years. It's kind of a snapshot of how is the US doing at mathematics. And this question was on the 8th grade and 12th grade assessments. And it was also the subject of a paper in the journal Science because kids did not do well. And what's interesting is when you look at this, you think, well, this is a fraction addition question. Every kid in the country at some point has been taught some procedure for fraction addition. So the fact that only 1/3 of high school seniors and 1/3 of 8th grade students got this correct is extremely worrying. The problem is that most of them, when confronted with a question like this, just like when I've used this question in professional development with teachers, I end up seeing a lot of things that look like this. You see butterflies being drawn, crisscrosses with smiles, all kinds of stuff happening. And the problem is that even if you do all of that procedural multiplication, if you do it everything correctly, you end up with 187 over 104. If you do not understand that 7/8 is about 1, there is very little chance that you're going to understand that 187 over 104 is actually about 2. So the problem here, this is not actually a question about procedural mathematics. Most of the kids, in fact, answered C or D. They added across the top or added across the bottom. And the challenge here is this really is a question about how well do you conceptually understand fractions? And the answer was not that well. Only about 1/3 of kids really had that conceptual understanding. So let's look at how we can rectify that. How can we actually teach this kind of conceptual approach? Because what we want is we want kids to look at this and go 7/8, that's about 1, 12/13, that's about 1. So therefore 1 plus 1 is still 2. So that's my answer. So here's a game. Here's Gigi on a wheel. Let's say I've got no idea what to do. I can drag this basket. I don't know. I'm just going to plonk it here and see what happens. Okay, Gigi got to 1. So, okay, I think I noticed I got it wrong, but I get the same problem again. So, okay, Gigi got to 1. I see a wheel. I'm going to see what happens. Okay, yes, I think I've got an idea here. Now I see 5 wheels. Okay, I'm going to, my perception action cycle is going to kick in. I'm going to make a prediction, see if I can start understanding this. I think Gigi's going to get to 5. And this looks like it's happening. Okay, so I'm starting to see how this works. It's kind of a relationship between these wheels and the number line. Now, I hasten to add, this sequence we're going to see is not a sequence that kids would actually see in ST Math. This goes a lot quicker. It's kind of a teacher's eye view of the learning path, as it were. But you can see now, okay, we can deal with little bits of a wheel. Here's a half of a wheel. Now we've got a really small fractional piece of a wheel. So, and now we've got a big change. Notice something very different has occurred here. Notice we can no longer purely use spatial reasoning to solve this problem because the information is now no longer given visually. it's given symbolically. Now we're going to see in a minute a game where we very specifically translate between visuals and symbols, but in this case, we've given it as symbols and we need to understand how this works. So, okay, a third, I'm basically graphing a third on a number line. Now I need to put 3/4 together. Okay, I got it. And now we do something else that we do a lot. We switch the way that we're asking the question. Notice if I try and click on the basket, I can't drag it anymore, but the other part of the screen is flashing. So it's like, okay, I need to choose how many of these bits of a wheel do I need to get to 2.5? How many halves make up 2.5? So I can do that. I can also ask this question symbolically. How many thirds do I need to get a little bit past 1? So basically I'm going to graph 4 thirds on the number line. And the complexity is going to keep increasing. So now we've got a bunch of 8s. They're going to roll out together. And now we can start adding fractional pieces. So I've got 1/3 plus 2/3. Okay, that's 3/3. So that's 1. And similarly, now I know what a half is. I know what 3/4 is. So now I can add fractions. This is not a game about adding the fractions using some kind of procedure. We have other games where you add fractions using common denominators, but this game is about estimating on a number line. And now students are in a position to do that. So that if they saw a question like 7/8 plus 12/13, they could go 7/8. I get it, that's about 1, 12/13. So that's really close to 1. Put them together, it's somewhere close to 2. So you can see how we can use a game-based learning system with a penguin to build this kind of deep conceptual understanding. And the interesting thing here, of course, is that ST Math is no longer just a couple of cute games or a little, couple of interesting sort of like oddities. It's actually, it's a very comprehensive, supplemental, but comprehensive curriculum. So just looking at 3rd grade, for example, here. There are 25 different objectives. We're going to look at one of these in detail because it's interesting to see just how deep we have to go to really build conceptual sort of underpinnings of this type of thing. So we're going to look at one of these fractions objectives and just kind of see kind of some of the key ideas here. So first up, notice there are 8 games in this one objective. There are also 203 puzzles students need to solve just to get through one objective. And do the math, there are 25 objectives. That means kids are going to solve many thousands of puzzles to get through one grade level. That is a lot of learning by doing, hands-on problem solving. That's what we do. And that's what, for kids, we're building their schema. The only way for kids to build schema like this is for them to actually do the doing and do the learning. So a couple of things to note. You'll see that the games are organized into levels. There's 6 or 8 puzzles in a level. If a kid gets a puzzle wrong, they get to do it again. But if they get it wrong twice, they get bounced out of the level, have to come back in, and we randomize the questions. So they can't just sort of learn their way through a sequence of questions. They have to kind of basically figure out what's happening. Now, notice we start all the way back with fractions. Even in 3rd grade, we're starting just, do you get that you have to have equal partitioning? So we always start with these really fundamental concepts. So even if a student is significantly below grade level, they'll be able to start here. This is somewhere all kids can get in. There's no language barrier to this. And here it's like, which one of these shapes is equally partitioned? Then we've got a game where they have to make those partitions equal. Now they're balancing halves and wholes, and other games with quarters and wholes. Another balancing game where when they're balanced, the monsters turn around and breathe fire. So lots of fun for kids. And then really interesting game. And we're actually going to look at this one in a little more detail because this is one of those games, and there are many in different places in the curriculum, where we very explicitly connect visuals and symbols. And this is a big deal because it's something we do repeatedly. And it's kind of, it's such a fundamental idea. We start everything visually, and then we very carefully connect whatever sort of visual schema we've built up with the math. We connect it to how the symbols work. And this is just a really good example of that. Basically, it's a virtual manipulative in this game-based shell. So here we're given 2/5 as symbols, and we have to build it. So we have a slider here. Notice as I drag the slider to my left, the denominator is increasing. So we've put the slider on the unit fraction. In this case, I'm going to put it to 1/5. And then once we've set the denominator, now we need to choose how many bits of this, these fifths do I need? And obviously I need 2 of them. And again, I get to test it, I get to see it. And if I get it correct, GG crosses the screen. Kids solve tons of these problems. They'll solve them with all kinds of different shapes. So we know they've got a real clear connection then between the visual and the symbolic. then we can go back and we can ask fractions in the context of all kinds of different shapes, because we want to make sure they've got connections all over that kind of schema space. Then very carefully building connections between circular fractions and visuals. And then just by the end of this one objective, we've built their schema to the point they can look at any fractional representation, visual fraction representation, and they can use symbols to name it and describe it. So that gives you some idea of kind of the depth that we go to when we're talking about schema building, building this for kids. This is what it looks like. It's very intentional, very detailed, but it has, you know, some really surprising, or I guess maybe not surprising ramifications. I've seen these charts, they call different things. I've seen them called quadrant D charts in some parts of the country, or rigor relevance charts. And it's a really good way of looking at math curricular or math kind of tasks that kids are being asked to do, and thinking about the rigor inherent in them, right? So basically, we've got an axis of thinking, kind of like a Bloom's taxonomy, basically, from, okay, is the math task mainly asking kids to sort of memorize things and regurgitate their knowledge, or is it asking them to use creative thinking to solve a problem? Is the math task a routine math task, or is it a non-routine thing that they maybe haven't seen before? And obviously what we want, what a lot of professional development is focused on with working with teachers. I know I did PD for many years in LAUSD myself. I was a high school teacher previously. And we want kids working up in this space. We want them solving, you know, using creative thinking to solve non-routine problems. The challenge is that a vast sort of amount of curricular materials are pretty solidly rooted in this bottom quadrant. So worksheets are all basically down here. Same problem 25 times, do a bunch of them, that's it. And obviously kids do need practice. They have to have those basic skills, but this cannot be your sole experience of mathematics. One of the problems when people say things like, why can't we teach it the way I learned it? They kind of learned it here and they don't realize that there is something else, and we need kids problem solving up here. And one of the, I think, the most powerful things with ST Math, or one of the biggest challenges, is even if you have curriculum materials that are asking questions up here, the language barrier for kids to get into this space is high. So what we can do with ST Math is we can remove that language barrier to this rigorous problem solving space. Now, suddenly all students from the very beginning, from kindergarten onwards, you saw that kindergarten problem, for example, all kids from the very beginning are rigorously using creative thinking to solve non-routine problems regularly. And that builds up a whole different approach to mathematics and learning. It's fun, it's enjoyable. And of course, one of the exciting things is that we do see transfer. You know, all of this would be for naught if we didn't see transfer onto the typical sort of math assessments that kids have to do. At the end of the day, yes, it would be great if we're building their schema with some visual thing, but it doesn't actually show any difference. But we do see a lot of difference, and it's exciting because we see that improvement, those gains for every different student subgroup, which is kind of what you'd expect. At the end of the day, if you can build kids' fundamental understanding of mathematics, guess what? They do better on assessments. It doesn't matter what assessment you give them. If they understand the math, they do better on it. And what's exciting is that's not only true for, say, gifted students who love this stuff because it's kind of, they can move at their own pace, really challenging questions and so forth and so on. But for special education students, this is huge. That removal of the language barrier is such a big deal. Obviously for English learners, all different subgroups, we see these types of gains. And of course, very importantly, kids like it. This is fun. This has obviously been a very tough year. I have two small children. I have a first grader and a fourth grader. They've been home for basically nearly a year now. And, you know, finding things that kids enjoy doing enough in terms of mathematical sort of programs that they want to do them is a big deal. And kids love playing ST Math. They find GG is fun and so forth and so on. And what's interesting, they don't just find it fun because, oh, the penguin's cute or something like that. Kids don't know the neuroscience, but they are aware that this is a little different. We see this type of response a lot in surveys. You know, GG helps me when I make mistakes, I'm learning. They sort of get this idea of productive struggle, even if they don't know how to name it. So it's almost like they understand that this is sort of, it's fun because it's hard, not fun because it's easy. So that's kind of an important point. And that goes to another piece of research that came out last year. Very, very exciting and interesting piece that I haven't seen anywhere else. And it looked at students' self-belief, how much they believed in themselves as mathematicians. And it showed that kids who played ST Math on a regular basis, putting in that time, basically problem solving, building their schema, learning through doing, learning that they can actually sort of, be very actively involved in that learning process, it changed their self-perception of them as mathematicians, which is a big deal because obviously a lot of kids are hearing very negative messages connected to mathematics from a very young age. And this impact was highest on the kids with lowest scores. So very significant research, something quite powerful. I think there's a lot more to come on that. So, one of the key ideas here, kind of going back to the memes, is times have moved on, times have changed. We no longer need kids to do math like a machine, we need them to build the machines. And that really is kind of what we're about here at Mind Research. We want students to come out as problem solvers, creative thinkers. And our mission is to ensure that all students are mathematically equipped to solve the world's most challenging problems. So hopefully that's given you a big picture, yet some interesting sort of looks at kind of what we do in terms of building a math game with a penguin, Gigi. So happy to, if we've got any little points we want to dive into and discuss, I'm more than happy to talk about that. But that's kind of at least a quick snapshot of what we do.
That was great, Nigel. Thank you so much. And I can say that as a former practitioner in Southern California, as an administrator, and then eventually moving to Illinois, and being a principal and chief of schools for Chicago Public Schools, I absolutely vouch for this. I have always put ST Math into the curricular programs of the districts and schools that I was leading, and saw tremendous results every time. Nigel, a couple of questions for you to kind of maybe help our audience understand how this fits into what they're and how they're teaching. Do you consider Mind to be their core math program? Is it a supplemental program? Do you guys consider yourselves an intervention program? How do they build that into their daily math schedule? So maybe a little bit of nuance on that could be really helpful.
Awesome, absolutely. No, great question. Thanks, Sean. Yes, you mean the practical realities of life, sort of thing, something connected with that? Yes. So ST Math is a supplemental program. So it's not core yet, although we are working towards that, but that'll be a couple of years yet. But so it's supplemental. The recommended amount of time for kids in second grade and above is 90 minutes per week. For kids in K1, 60 minutes a week. And schools find a wide variety of ways of fitting that in. There's all kinds of different things. Some schools obviously will sort of start using this, thinking of it in intervention terms with special education students and English learners. But in general, what we find is that schools that start there, after a bit of time, realize, oh, actually, this will benefit everybody. And this is very much designed as an all student program. This is not something that only works in certain circumstances. This is very, the learning math in a way that helps you to really deeply understand it is valuable for all kids, even if they're already showing signs of being very good at math. This is, in fact, then just doubles that up and enhances it even more. So 90 minutes a week is basically the bottom line in terms of getting kids to have that time on task.
That's great. Yeah, I think that's really helpful for our members and audience that are kind of thinking about this. The other kind of question that we often get a lot is, how do you think about kind of the core software experience matching the scope and sequence of the textbook? Do they need to be the same lessons? Do they not need to be? I know you've got years of thinking around this, and it tends to be a question on a lot of people's minds. So tell us a little bit about how you think about that.
That's a great question. And it's something that comes up a lot because a lot of people obviously are very used to the idea with, supplemental programs, whatever, this idea of, okay, we're doing this in our book this week or this month or whatever, so I'd like to do this. And that's totally fine. You can absolutely order ST Math or even make assignments of objectives to match that kind of ordering. But the thing that I think is a little bit less understood is that we're really about building schema, which actually takes significant time. Kids are not going to, it's not just a question of sort of learning an idea. It's really this building this connected web of schema with, say, fractions is actually going to happen slowly over, many months, if not a couple of years. So it matters a little bit less whether or not, in an ideal world, kids would probably go through and do the ST Math stuff first before they get to it in the classroom. because that way they've kind of built a lot of the conceptual underpinning of what they're then seeing. And certainly we've had a lot of anecdotal evidence, if you like, of teachers saying, wow, this, teaching subtraction across tens or something like that, used to take me 2 weeks in second grade. Now it took me 2 days because the kids had the basic sort of idea. Literally, they had the schema. So schema building is subtle. It's a little different from the way that we're used to thinking about sort of teaching and ordering content. But really speaking, it doesn't matter that much. The main thing is the time on task is more important than whether or not it's exactly matched to. We have a visitor joining us today. My cat has just decided to drop in and try and
That's all right.
disrupt proceedings.
Well, yeah, no, I think that makes a lot of sense. A lot of the teachers that implemented the program when I brought it in multiple different contexts and districts used to always kind of label that as pre-teaching. And they said that they could always see the kids that had done the GG math lessons before they introduced the units because they would get it like that. And so,
Right.
the pre-teaching is almost a way of building that foundation of the schema to get to those other things. So I think those are great points. The number one question we're getting right now, and this is going to be no surprise to you, is remote learning. So how does
Yes,
ST Math and Mind work for school districts that are doing remote learning or distance learning right now?
Obviously, fantastic question. Yes, it's a question that we get a lot and have to deal with. And it works obviously fantastically. I mean, it's because primarily the ST Math portion of it is something that kids do one-to-one. And the fact that they like it is huge because one of the challenges, like I kind of mentioned, is teachers can assign kids a program, but if they really don't enjoy doing it, they're going to struggle to do it when there's sort of less supervision. So the fact that kids actually enjoy doing this, we, for example, saw that after last March, when kids predominantly went out of school, the number of weekly average minutes per student in ST Math went up by nearly 15 minutes. It went from like 57 to 75 or something like that. So the point being, when they had to sort of do it less, they actually ended up doing it more because they actually enjoyed doing it. So that's a big deal. I mean, fundamentally, it's like, wow, they actually liked it. So, and that, we found traditionally every Christmas, for example, we get this spike in usage on the day after Christmas Day as kids open their iPads and sort of go, oh, I'm going to play Gigi. So we do see that because kids like it, they will do this. And then, of course, we have a whole host of number talks, math chats, all these other sort of tools which are really useful for then working remotely with students. And teachers have data, they can track students, figure out who might be struggling somewhere. So we have all of that kind of practical stuff that enables teachers to actually use the program remotely. But fundamentally, kids like playing it, therefore they will actually do it. And I think that's almost the biggest bottom line thing when it comes to remote learning is they will actually do it and they will be learning. This is not a practice program. This is a you're going to learn program. And I think that's a big deal.
That's great. Yeah, absolutely. So I'm going to we're almost out of time. I'm going to bring my colleague in, Garrett, to see if he's got any follow-up questions. And as he's kind of coming in, Nigel, the last question that we always get is how do they contact you? So I don't know if you've got a slide that we can bring up or we can kind of make sure that we put that information kind of in our follow-up to all of the folks that kind of view the webinar. We just want to make sure that they can get in touch with you. So we can, if you don't have that, we can make sure we embed that in as we allow our audience to watch on demand. While you're kind of
you mean
I'm going to bring in Garrett. See if he's got any other questions.
Yeah, I think, virtually, what's the best way to engage? And that was my follow-up as well. If there's any content that we can share out to our audience that may be helpful as they're thinking about this, kind of to experience it virtually, or any type of demos that they could check into, we'd love to be able to share those as well.
So the best way by far is, and I know it kind of keeps disappearing from the screen, but it is there quite a lot, stmath.com. There's a blog section which has got all kinds of, there's podcasts about STMath, there's tons of articles, talking about different aspects of the program, all the way from stuff about how to implement to the neuroscience behind it and so forth and so on. So there's a ton of stuff there. And then obviously also through there are ways of contacting and reaching out to any different people in the organization for whatever the needs might be. So yeah, stmath.com is probably the simplest way of accomplishing most of that. And as I said,
That's
there's
great.
a blog, there's all sorts of stuff.
Yeah, and we would highly encourage folks to watch or to go on to stmath.com and to be able to get more information out about this. So Nigel, thank you so much for leading us through our first thought webinar of 2021. We would absolutely love to invite you back in the future. You have been fantastic. You have definitely, I'm sure, piqued our audience's interest. And my guess is lots of folks are going to be getting onto the website right now to kind of check this out. And we appreciate you being part of the Futures Institute here in 2021 and really talking about the future of how kids are learning. And I think there's no better organization than Mind Research Institute that is well positioned to help us think about teaching math from a perspective of building kids' schema. I love that, and that's one that I'm going to walk away with. Garrett, anything else from your end before we end today's broadcast?
Just want to thank Nigel for joining us today and look forward to the next time we get to connect.
Pleasure. Thanks, guys. Thank you very much.
Wonderful. From all of us here at the Futures Institute, my name is Sean, my colleague Garrett. Our guest host today was Nigel Nisbet from the Mind Research Institute. We look forward to seeing you back here on demand from wherever you are across the United States or across the globe, featuring our 2021 Thought Leadership webinars from the Futures Institute. Thanks, everybody. Have a good day.